different. So in this problem, I have two buffers. Both of them are the same substances. I have acetic acid and sodium acetate. One of the buffers, I have 5 molar of each. The other buffer, I have 0.05 molar of each. So this one's 10 times the concentration of that one. But both the acidic and basic portions are the same concentration. So first, I'm going to start by finding the original pH of just my buffer. So let me do that. So the way that you would do that is you would write out your equations. The dissociation of the sodium acetate and the dissociation of your acetic acid. So I'll do that maybe here. So my sodium acetate is NaCH3COO. That fully dissociates into Na plus and the acetate ion. And then I have my acetic acid, CH3COOH. That dissociates partially to give H plus and the acetate. All right. And if I want the pH of this buffer, I have two options. I could either do an ice chart for my acid dissociation here, find, plug it into the K expression, find my X and all that stuff, or I could use the Henderson-Hasselbalch. So I'm going to go ahead and use the Henderson-Hasselbalch. So for the first buffer, I'm going to say pH is equal to the pKa. pKa is negative log of the Ka, which probably by now you know what the Ka for acetic acid is 1.8 times 10 to the negative fifth, plus log of my conjugate base, which is in this case the sodium acetate, it's 5.0 molar, over the concentration of the acid, which is the acetic acid. It is also 5.0 molar. So take a look at this. These two concentrations are the same, so 5 over 5 is equal to 1. What is log of 1? It's 0. When my conjugate base and my acid are the same concentration, turns out that the pH is going to be equal to the pKa. So the pH is just negative log of the Ka here, which in this case ends up being 4.74. Okay, let's do it for buffer B. So the pH is negative log of the Ka, or pKa, so it's still acetic acid and sodium acetate, so the same Ka, plus log of my conjugate base, which is the sodium acetate. It's now 0.05 molar, and my acetic acid is 0.05 molar. What happens to the pH? It's the same. 4.74 is my pH again, because it doesn't matter what the concentrations are, as long as they're the same concentration. Then when you divide them by each other, the acid and the conjugate base, it's equal to 1. Log of 1 is 0, and so the pH is equal to the pKa. So whenever you have a buffer and you have an acid and its conjugate, or a base and its conjugate, but they're both the same concentration, the pH will always be equal to the pKa, or the pOH will be equal to the pKb. All right, now what I'm going to do next is I'm going to add 0.01 moles of HCl. And I'm going to add that to a liter of my buffer. And I'm going to decide what happens to the pH. So in order to do that, first, you have to decide what reacts with what. So I like to draw my little beaker. So my beaker here, I have my acetic acid, CH3COOH, I have my sodium acetate, NaCH3COO. And I'm going to add some HCl, so that's really H pluses, so I'm putting in some H pluses. What's going to react? Well, H plus is an acid, so it's going to react with the basic portion of it, which is this. And I wrote sodium acetate. I probably should have just written acetate ion, so I'm going to cross out the Na there and put the negative here. You know, if you want to put your sodium, you can. It doesn't really matter. It's a spectator ion. So I'm going to start by writing my reaction that happens. So for both A and B, your H plus is going to react with the acetate ion. And guess what product you form? You form acetic acid. I'm going to write this twice. One time for A, one time for B. Because even though it's the same reaction, my numbers are different. Because my concentrations are different. So, let's see. My H plus looks like I'm adding 0.01 moles in a liter, so that's 0.01 molar. And that's for both of them, for both buffers. I'm adding 0.01 molar of the H plus or the HCl. For my first buffer in A, my concentrations of the acetic acid and the acetate are both 5 molar. So this is going to be 5.0 molar, and this is 5.0 molar. For B, both of them are 0.05 molar. All right, let's start with A. So looking at these, which one's my limiting reactant? Looks like I have a lot less of this one, so that's my limiting reactant. So that's how much is used up. So minus 0.01 molar, minus 0.01 molar, plus 0.01 molar. And so this at the end, I end up with 0 H pluses. I have 4.99 molar of this one, and I have 5.01 molar of that one. So if I want to find the pH, I'm going to use the Henderson-Hasselbalch. It's pKa plus log of the concentration of the conjugate base over the acid. And so for A, I am going to say pH is equal to negative log of the Ka, which is 1.8 times 10 to the negative fifth, plus log of my conjugate base, in this case, is my acetate is 4.99. My acid is acetic acid 5.01. Calculate that. I end up with 4.74. Okay, I'm going to do the other one. I'm going to do it in blue here. So, I said that I have 0.01 moles of my H pluses, 0.05 molar of both of these. Let's compare these. Which one's my limiting reactant? Still the H plus. And so, minus 0.01 molar, minus 0.01 molar, plus 0.01 molar. So at the end of this reaction, I end up with 0 H pluses, and then 0.04 molar and 0.06 molar. So to find the pH, I'm going to use the Henderson-Hasselbalch. And again, if you want to use an ice chart, you're more than welcome to do that. Just the Henderson-Hasselbalch is a little bit easier. So pKa, which is negative log of the Ka, plus log of my conjugate base is 0.04 molar. My acid is 0.06 molar. And so if you calculate that, you end up with 4.55. My initial question was asking what change in pH happens when you add that 0.01 moles of HCl to these two buffers. And so looks like if I add my acid to my first buffer, pH remains the same. It was 4.74 initially. Let me move it down a little bit. So my first buffer in A was 4.74 initially, remained as 4.74. My second buffer started out as 4.74, went down slightly, 4.55. Not a significant difference. A significant difference would be probably a change of a pH of 1. So it's not significant, but it definitely changed. So both have good buffering capacity for my amount of acid, but which one has a better buffering capacity? Well, obviously it's A. So let's take a look at the differences between A and B. Well, A had a lot more stuff in it, a lot more buffer in it. It's 5 molar compared to B was, 0.05 molar. So definitely a big difference there. Alright, so we looked at the calculations with the buffers. Next, let's say I want to make a buffer. How would I go about making a buffer? Let's say, I need to hold a system at a certain pH. How would I do that? Your body has a lot of buffers. Your blood, for example, has a lot of buffers in it, like the bicarbonate ion, for example, in your blood system to keep your body from changing pH so much. So, two things that you need to consider here. It has to have enough stuff to resist changes to pH based on how much acid you're adding or how much base you're adding. And you need to pick a pH that would hold it at the desired pH. So, if your blood is slightly basic, I think it's like 7.2 to 7.4 or something like that is its pH, slightly basic. You want to have a buffer that is slightly basic, that is going to hold the pH at that level, not, something that's way higher or way lower. So, let's say I want to make a buffer that will maintain the pH as 4.3, which means that I want my H plus concentration to be 10 to the negative 4.3, which ends up being as 5 times 10 to the negative fifth. So I would want to pick a buffer that's acidic because, that's an acidic pH. So I want to pick a buffer that is an acid with its conjugate base. So a weak acid and its salt, as opposed to a weak base and its salt, since this is acidic. And I want to pick my weak acid to have a Ka value that's something times 10 to the negative fifth. You want your weak acid in your buffer to have the same Ka value as close to the Ka value as your H plus concentration that's desired. So let's actually do a problem. So this one says, how would you prepare a buffer that's made of acetic acid and sodium acetate that will hold your pH at 5.00? So let's try to think about this. I know that I'm going to use acetic acid and sodium acetate. And I know that my Ka expression is going to be the concentration of the H plus times A minus over HA. or, if I'm using acetic acid and sodium acetate, let me rewrite that. I want it to say H plus times, the A minus in this case would be the acetate ion. The HA would be your actual acid, acetic acid. All right, well, what do I know from here? Well, I know the Ka of acetic acid, right? I can plug that in. I also know what I want my H plus concentration to be because I know what the pH is. So I know that the pH should be 5.00, which tells me that I want my H plus concentration to be 10 to the negative 5.00. So, same thing as 1.0 times 10 to the negative fifth molar. So I know my Ka value. So I'm going to go ahead and plug that in. 1.8 times 10 to the negative fifth. And I also know my H plus concentration. I want it to be 1.0 times 10 to the negative fifth. And my acetate ion concentration goes here. My acetic acid concentration goes there. If you were to move this value to the other side, it would go in the denominator, right? So let's rewrite that. That would be 1.8 times 10 to the negative fifth over 1.0 times 10 to the negative fifth is equal to the concentration of the acetate over the concentration of the acetic acid. If you divide that, that ends up being 1.8, right? Which is the same thing as like 1.8 over 1. What is that telling you? That's telling me that I want to make this buffer so that my acetate ion concentration would be 1.8 times the concentration of my acetic acid. It doesn't matter how much I use. It doesn't matter what the volume is. As long as the acetate ion concentration is 1.8 times the concentration of my CH3COOH, that's fine. So if I, for example, make the acetic acid 1 molar, then the acetate ion would be 1.8 molar. So if I say that I want to make 1 liter of my solution, what I would use is I would figure out what 1.8 moles of the sodium acetate is, and I would use 1 mole of the acetic acid. If I mix those together in a 1 liter volumetric flask, I should get a pH of 5.00. Let's try another one. So this problem says how much KOH must be added to a 1 liter of 2 molar acetic acid to make a buffer with a pH of 5. Now, it's a hard question. It's hard to figure out what to do first, but there should be something that's really bothering you about this question. When I first read this question, it really bothers me because it's asking how much potassium hydroxide I'm adding to acetic acid to make a buffer with a pH of 5. What's a buffer? A buffer is a weak acid and its conjugate, or a weak base and its conjugate, right? So I have a weak acid here, but I don't have its conjugate anywhere. I have acetic acid, but nowhere do I have acetate. If I have acetic acid and I want to make a buffer, I need some acetate there. Potassium acetate, sodium acetate, lithium acetate, anything with acetate to make it into a buffer. And so there's no buffer. How can I make a buffer if I don't have, my conjugate there? Well, you can. You just gotta wait a little bit and see what's gonna happen. So, right now, I don't have a buffer. All I have is KOH and acetic acid. I'm gonna mix them together to figure out how much KOH I need to add, right? Well, let's write the reaction that's going to happen. In chemistry, whenever they're talking about a reaction, you're mixing two things together, write the equation first. So my KOH, I don't care about my potassium. It's a spectator. It's OH minus that's reacting here. I'm going to mix that with my acetic acid. And what would I form? Well, this is a base. This is an acid. A base is a proton acceptor, so it's going to grab an H plus from the acetic acid to form water. And then the acetic acid is going to donate an H plus to form acetate ion. So I'm going to form water and acetate ion. And once I do that, look at that. Now, if you have some leftover of this and some of this formed, I would have made a buffer. Isn't that cool? I thought that was really cool when I first looked at this problem. So anyway, what am I asked for? I'm asked for how much of my KOH I'm adding. So really how much of the OH minus I need to add. So since I don't know how much I need, let's call that X. Okay. I know how much acetic acid I have. I have 2 molar. So I'm going to write 2 molar here. I don't care about my water. My acetate to start with is 0 because I didn't start with any acetate. I just started with my acetic acid and my potassium hydroxide. Well, what's going to be my limiting reactant? If I'm asked how much KOH I need to add to this, then that means I need to use up all my KOH, right? I should not have extra OH minuses floating around. So if I start out with X here, X is going to get used up. So I end up with a little bit of this and a little bit of this so I can make a buffer. So I'm going to say my change is X. So minus X plus X. So at the end of this reaction, I don't have any leftover hydroxides. I have 2 minus X of this and X of this. So you can use your Ka expression if you would like, or you can even use the Henderson-Hasselbalch if you want. It's totally up to you. I'll use my Ka expression. Ka is the concentration of the Ka for acetic acid is the concentration of the H plus times concentration of the acetate over the acetic acid. My Ka is 1.8 times 10 to the negative fifth. That's not going to change for my acetic acid unless you change the temperature, which we're not. My H plus, I know I want my pH to be 5, so that means that my H plus concentration needs to be 10 to the negative fifth, which is 1.0 times 10 to the negative fifth molar, basically. So that's my H plus, 1.0 times 10 to the negative fifth. And then my acetate needs to be X. My acetic acid needs to be 2 minus X. Look at that. You can solve for X. X. This is just basic algebra. You don't need a quadratic for this or, the intersection or anything like that. This is just basic algebra. If you solve for x, that ends up being 1.29 molar. And so that should be my starting concentration of my hydroxide, which is my starting concentration of my KOH, because everything's a 1-to-1-to-1 ratio. And so 1.29 moles per liter of the KOH. I'm going to change that to grams. 56.1 grams, I believe, is the molar mass. And my buffer is 1 liter, 0.00 liters. And so that ends up being 72.4 grams of KOH.